Okay, thank you. All right, so there's a bunch of stuff that I need to do for formality's sake first before we get back to these quadrature points. First thing I want to do is talk about Legendre polynomials. All right? So what's a Legendre polynomial? So the Legendre polynomials are the solution or the solutions to Legendre's differential equation. And Legendre's differential equation looks like this, which is d by d tau of 1 minus tau squared d by d tau of Pn of tau plus n times n plus 1 Pn of tau equals 0, and that goes for n equals 0, 1, 2, and etc. So the Legendre polynomials, when you actually solve this differential equation, the solutions Pi of tau are given as follows. P0 of tau is equal to 1. P1 of tau is equal to tau. And from this point forth, then all the others are given by this recurrence relation. Which is n plus 1 times p n plus 1 of tau is equal to 2n plus 1 times p n of tau minus n times p n minus 1 of tau, which is why you need the first two. All right, now, these are defined, the Legendre polynomials, are defined on tau in minus 1 to plus 1. That's how they're defined. And they have the property that the integral from negative 1 to 1 of pi of tau, pj of tau, is equal to 2 over 2j plus 1 times, well, delta ij, where delta ij is equal to 1 if I is equal to j and 0 if I is not equal to j. So they're orthogonal to one another. So that means that these polynomials are orthogonal on tau in minus 1 to plus 1. So that's the first thing that I want to talk about, okay, Legendre polynomials. Now, the thing about Legendre polynomials that you have to realize is that because they're orthogonal, suppose that f of tau is a polynomial of degree at most n minus 1. Okay, so it's at most n minus 1. Then you can write f of tau as a linear combination like this: I equals 0 up to n minus 1 of ci times pi of tau, because the first Legendre polynomial is a constant, the second one is a linear function, the third one's a quadratic, et cetera, et cetera, et cetera, right? So you can write it this way. So you could see that if I take the integral of f of tau, Pn of tau d tau, from negative 1 to 1, that's equal to the integral from negative 1 to 1 of the sum from I equals 0 up to n minus 1 of ci pi of tau times Pn of tau d tau, which is equal to the sum from I equals 0 up to n minus 1 of ci times the integral from negative 1 to 1 of pi of tau, pn of tau, d tau. But I goes from 0 to n minus 1, so that's equal to 0, which means that any polynomial of degree n or higher, or n, actually just stick with n, must be orthogonal to all the Legendre polynomials up to n minus 1, right? So this polynomial, because it's a degree at most n minus 1, the nth degree Legendre polynomial is going to be orthogonal to any polynomial that's degree n minus 1 or less. Doesn't matter what that polynomial is, okay? It's always going to be, because this polynomial can be written as a linear combination of the Legendre polynomials, okay? So that's the next property. The next thing I want to talk about, by the way, this is all building blocks for other stuff, okay, are what are called Lagrange interpolating polynomials. Okay. So suppose that g of tau is an arbitrary function on tau in minus 1 to plus 1. Okay, just take some function. And also, let tau 1 up to tau n be a set of distinct points on tau in minus 1 to plus 1, same interval. Okay? Then what we can do is we can define, I'm going to get back to g of tau in just a second. So we define the following basis, or define the following set, the following functions. These functions are Li of tau, which is equal to the product from j equals 1 up to n, where j is not equal to I, of tau minus tau j, all divided by tau I minus tau j. The functions Li of tau for I equals 1 up to n are called Lagrange interpolating polynomials. Or just simply Lagrange polynomials. Call them Lagrange interpolating polynomials for a reason. So now, if you take these polynomials, you'll see that they have the property. The functions Li of tau have the following, what's called isolation property, which is that if I evaluate Li at any of the support points, tau j, where tau j is from that set there, then this is equal to delta ij, which again is equal to 1 if I is equal to j, and 0 if I is not equal to j. Okay? So what that means is that if I take any of these polynomials and I evaluate it at any point other than the entry in the basis itself, I got this basis of polynomials L1, L2, L3, all the way up to Ln. If I take the ith one of those and I evaluate it at any support point other than the ith support point, I'm going to wind up getting 0, right? It doesn't mean it's true at all points in the interval. It means that if I choose that set of support points and evaluate the ith polynomial at any of these support points, the only one that produces a non-zero result is the support point that matches that particular polynomial. Because if you look at the way this thing is constructed, you'll see that that has to be the case. All right, now, given the fact that that's true, we can then approximate g of tau using the Lagrange polynomials as g of tau is approximated by this function big G of tau, which is equal to the sum from I equals 1 up to n of Ci Li of tau. It's an I. Now, if you look at that approximation, you'll see that, let's suppose that I stuff in tau j into that. So if I take g of tau j, which is approximated by g of big G of tau j, that's going to equal the sum from I equals 1 up to n of Ci times Li of tau j. But Li of tau j is equal to delta ij, right? So this is equal to the sum from I equals 1 up to n of Ci delta ij. But delta ij is only going to equal 1 when I is equal to j, right? So this is going to equal Cj, which means that Cj has to equal g of tau j, which means that this approximation g of tau equals the sum from I equals 1 up to n of g of tau j times Li of tau. Now, if you take that result and you just do like a sort of schematic plot, this is what you get. This is what makes Lagrange interpolating polynomials useful, is that I've chosen a set of support points, tau 1 through tau n. So let's mark them on this plot here. Here's my interval from -1 to +1. This is tau. And let's just choose a bunch of points here. Tau 1, tau 2. I haven't told you what these points are. I'm just going to pick a bunch of points here. Tau 3, all the way out to tau. Tau n. Okay? These points could include the endpoints of the interval. Now let's suppose that this is my function. This is g of tau. Okay? So I got this function here. So you can see that the values of g of tau j are here. So this is g of tau, little g of tau. It says that my approximation, which is big G of tau, has to satisfy the condition that it must pass through these particular points. But everywhere else, it's not necessarily going to equal that particular function, right? It just means that at the support points, it's equal, right? So this here is big G of tau. And you can see from the graph that little g of tau j has to equal big G of tau j, all right? Now, we need both of these things. This is why I went through all this stuff, okay? So we've gone through Legendre polynomials, and we've gone through Lagrange polynomials. So now we're going to get back to Gaussian quadrature, all right? So Gaussian quadrature and the methods I'm about to explain, which get back to optimal control, but you're not going to understand these methods until I go through all this stuff, are predicated on using Legendre polynomials together with Lagrange polynomials in order to construct high accuracy approximations to integrals in order to be able to solve optimal control problems. So that's the basis for all this. What we have is we have this set of functions which I'm using as interpolants. So these are the Lagrange polynomials. I have these Legendre polynomials which I need in order to be able to do something else. And I'll show you what that something else is in just a minute. And that gets back to what Gaussian quadrature is, all right? So Gaussian quadrature utilizes information from Legendre polynomials. Why does it use information from Legendre polynomials? Well, the reason is as follows, is that suppose that, well, let me put a title on this. Accuracy of Gaussian quadrature. Okay. Now, suppose we do this. Suppose that we want to integrate a function g of tau, where tau is on -1 to +1, as the integral from -1 to +1 g of tau d tau. Okay? But we're going to do this by approximation. Okay? And assume now that the integral will be approximated by an n-point quadrature, which looks like this, where we say that the integral from -1 to +1 g of tau d tau is going to be approximated, it's an approximation, by the sum from I equals 1 up to n g of tau I, put in the right order, wi g of tau I. Okay? I'm going to use endpoints. I've got these weights, and I'm going to do this approximation. So what we're going to show is as follows. This is why Gauss quadrature is so useful. Okay? Which is that we know that, suppose now that g of tau is a polynomial of degree at most 2n minus 1. Okay? So g of tau is a polynomial. It can be up to a polynomial of degree 2n minus 1. We know that, and further, let tau 1 up to tau n be the zeros, or the roots, of the nth degree Legendre polynomial which of course is p sub n of tau. All right? So what that means is that if I evaluate Pn at tau I get 0 for I equals 1 to n. Okay? Because they're the roots of that polynomial. It's an nth degree polynomial. It has n roots, right? They happen to all be real. Okay, so I've got these points. So now, I'm going to do this. This is like my sort of backwards way of doing this. But let's suppose that I do this. This is division. Okay, you can't actually do this. This is schematic. Okay, so if I divide Pn of tau into g of tau, right, I get this quotient. I'm going to call this quotient f of tau. If I then multiply this, I'm doing hokey division here. You can't actually do this, right? I mean, this is like, you can do it, but you know, you have to be careful. So Pn of tau times f of tau. And if I subtract, what do I get? I get g of tau minus Pn of tau times f of tau, right? And suppose I call that h of tau. So what you can see is, if I rearrange that, I've got a quotient and I've got a remainder. So what I can write is that g of tau is equal to Pn of tau times f of tau plus h of tau. Now, given the fact that this function g of tau is a polynomial of degree at most 2n minus 1, if I divide it by a polynomial of degree n, what can f possibly be at most? Taking a polynomial of degree 2n minus 1, I'm dividing it by another polynomial of degree n. So what's the maximum degree that the polynomial f of tau can have? N minus 1, right? So this implies that f of tau is of degree at most n minus 1. But if you look at the result here, you'll also see that when I do this subtraction, this thing over here, this h of tau, which is the remainder, also has to be of degree at most n minus 1. So both of these things have to be of degree at most n minus 1. So now, given the fact that I can write this polynomial of degree 2n minus 1 this way, now let's integrate this. Let's integrate this polynomial. So the integral from negative 1 to 1 of g of tau d tau is equal to the integral from negative 1 to 1 of Pn of tau times f of tau plus h of tau d tau, which is equal to the integral from negative 1 to 1 of Pn of tau times f of tau d tau plus the integral from negative 1 to 1 of h of tau d tau. Right? I just broke that up. But what's the degree of f of tau? What's the maximum degree it can have? N minus 1, right? And we know that the nth degree Legendre polynomial is a polynomial of degree n, right? And the nth degree Legendre polynomial is orthogonal to all polynomials of degree n minus 1 or less, right? So the integral from negative 1 to 1 of Pn of tau times f of tau d tau has to be 0 because Pn of tau has to be orthogonal to f of tau because f of tau is a polynomial of degree 1 less than p, at most 1 less than Pn of tau, right? And this is the nth degree Legendre polynomial, so this whole thing is 0. So this gives you the integral from negative 1 to 1 of h of tau d tau. Okay? That's the first thing we need to get straight. So the next thing that we do is we make the following observation. Next, we know that tau 1 up to tau n are the roots of Pn of tau. So that means that if I evaluate g at tau I, or any one of these values, what do I get? I get Pn of tau I times f of tau I plus h of tau I. But tau I go from 1 up to n, and they're the roots of Pn of tau, so this term here is 0, right? Which means that g of tau I has to equal whatever the remainder is at tau I, right? So what that says is it says that I can replace, if I'm doing this now with a quadrature, what I can do is I can replace, make the following substitution, which is that I know that, so we know that h of tau, because h of tau is a polynomial of degree at most n minus 1, right? So I can replace it with another polynomial of degree at most n minus 1, right? So I can replace it with a Lagrange polynomial basis where I use the support points tau 1 through tau n. So this is equal to the sum from I equals 1 up to n of h of tau I times Li of tau, where Li of tau are the same Lagrange polynomials that I defined before. J equals 1, j naught equal to I, 1 to n, of tau minus tau j, all divided by tau I minus tau j. These are all taus. Okay? So if you look at that, now what you can do is this. Is you can say that the integral from negative 1 to 1 of g of tau d tau is equal to the integral from negative 1 to 1 of h of tau d tau. But h of tau d tau is equal to the sum from I equals 1 up to n of what? Of h of tau I times Li of tau d tau. But h of tau I is equal to g of tau I. So this is negative 1 to 1, the sum from I equals 1 up to n of g of tau I times Li of tau d tau, which is equal to the sum from I equals 1 up to n of g of tau I times the integral from negative 1 to 1 of Li of tau d tau, which is equal to the sum from I equals 1 to n of Wi g of tau I. So what have we done here? We've said that where those w's are, for completeness, let's write that out. Where wi, which is equal to the integral from -1 to 1, Li of tau d tau, is the quadrature weight. So what we see here is that this approximation, because remember I said that g of tau is a polynomial of degree at most 2n minus 1. So since I can break it up this way, when you actually do this, when you do this decomposition in this manner, what you see is that you can write this as an endpoint quadrature if you're approximating it, and it's exact. Because the only thing that's, because I haven't made any approximations in here. You see that? See, this right here is not an approximation. It's an exact replacement because this is a polynomial of degree n minus 1. I'm replacing it with n minus 1 polynomials of degree n minus 1. So this is not an approximation. It's exact. It doesn't say h of tau is approximately this. H of tau is equal to this. Because it's equal to that, and because I know that the original function was a polynomial of degree 2n minus 1 or less, it means that this approximation based on this remainder, where the remainder evaluated at each of these points is equal to the original function value at each of those points, means that this right here is an exact representation provided that that function is a polynomial of degree 2n minus 1 or less. Okay? I get an n for n points. I can approximate this with an n-point quadrature, but that approximation is exact as long as that polynomial is of degree 2n minus 1 or less. So what this says is, it says that the quadrature approximation using the LG points as the support points is exact, provided that the function being integrated I should be more careful here. The n-point quadrature approximation, provided that the function being integrated is a polynomial of degree 2n minus 1 or less. So that's a pretty powerful statement, because what it's saying is that if I choose the points correctly, if I say I got these support points, I'm going to use these support points in a manner that those support points are going to be the zeros of the nth degree Legendre polynomial. If they are the zeros of the nth degree Legendre polynomial, if I only have n of them, I can exactly integrate a polynomial of degree 2n minus 1 or less. So I can integrate a polynomial of almost double the degree for half the points, right? I mean, if I actually got double the degree, I'd be able to integrate a polynomial of 2n, right, for n points. But I can't do that. So I get 2n minus 1. So I'm off by 1. But you can see that as the polynomial degree increases, this becomes an extremely good approximation, provided that that function can be well approximated by a polynomial. So if I have an arbitrary function, if it's a smooth function, because this doesn't work, if the function's not smooth, polynomial approximations aren't good, right? If the function is smooth, it says that, eventually in the interval -1 to 1, there will be some degree polynomial that will be a decent approximation to that function, right? Maybe a straight line doesn't do it, maybe a quadratic doesn't do it, but a third, fourth, fifth, sixth, seventh, eighth degree polynomial, eventually you get to the point where you can actually construct a reasonable approximation with some polynomial of reasonable degree. You don't have to go to a 200th degree polynomial. As long as you can do that, you can integrate this with many fewer points than the degree of the polynomial. So if the polynomial is of degree 20, right, that's the polynomial I've got. 2n minus 1 is equal to 20, which means n is equal to 19 over 2, which is approximately 9, which means if I use 9 quadrature points, as long as I've chosen those 9 quadrature points to be the LG points, I can integrate a polynomial approximately, integrate a polynomial of degree 20, right? I really need 10 quadrature points because 2n minus 1 equals 20 gives you 2n equals 19, which gives you which gives you n is equal to 9.5. So you really need 10 points, right? So approximately 10 points. But you get an exact evaluation of the integral. So that's important when we get back to optimal control, because remember, we're trying to integrate functions, and we need to integrate the cost function, we need to integrate the dynamics. So we have to have a way of being able to do all this in an accurate manner, and we want to use as few points as possible in order to be able to do that approximation. Okay, now let's do one more thing before we finish. I did this all for Gauss, so I want to do one thing here for Redau. Okay, so the last thing I want to talk about is Redau. For some stupid reason, I don't have those sheets. I don't really need them, but it doesn't matter. So, let's see over here. Okay. So now let's talk about Legendre-Gauss-Redau points. Okay. So, and then we'll do Legendre-Gauss-Lebesgue points. So, suppose now that tau 1 through tau n are the roots of Pn of tau plus Pn minus 1 of tau together with the constraint that tau 1 has to equal negative 1. Okay? These are what are called the Legendre-Gauss-Redau points. So these are the LGR points, or Legendre-Gauss-Redau points. So when you construct a quadrature now, you can see that if I'm constraining tau 1 to equal negative 1, how many points do I have left that I can actually choose? Right? I've chosen them to be the roots of this polynomial, but if I didn't choose these points to be the roots of this polynomial, if I just tie down tau 1 equals negative 1, but I'm going to use an n-point quadrature, how many points would I have free to be able to figure out what they are? N minus 1, right? So the thing is that with the LGR points, one point, or one endpoint, is constrained. Which means that there are n minus 1 points that can be chosen and we take these points to be the roots, or the interior roots, of Pn of tau plus Pn minus 1 of tau. Now, if you remember, with Legendre-Gauss points, we didn't constrain any of the points. We said we have n free points. Now we're going to let the points be the roots of this particular polynomial, of the nth degree Legendre polynomial. If I now say that the roots of the freely choosable points, I'm going to say that they are the roots of this particular polynomial. I have n minus 1 points that I was allowed to be able to pick. I picked them to be this way because I can't pick tau 1. Tau 1's been fixed at negative 1. I have no choice on what tau 1 is. All right? So given the fact that I've now reduced the number of free points from n to n minus 1, if Gauss could integrate a polynomial of degree 2n minus 1 exactly with n free points, right, which I chose to be the roots of the nth degree Legendre polynomial, now I have n minus 1 points that I can choose. I choose them to be the roots of this other polynomial. What's the best polynomial, what's the best integral approximation I can get with Redau? I have one fewer point. So I can get one less degree accuracy than I could get with Gauss. Gauss gives me exact for polynomial of degree 2n minus 1 or less. If I now have one less point that I can actually freely choose, then I have one less degree accuracy than I can get. So I've eliminated 1 degree of freedom, so I eliminate 1 degree in the accuracy, which means that LGR can integrate a polynomial of degree 2n minus 2 or less using the n LGR points. And the proof goes exactly the same way that this other proof goes. You just start with the same kind of approximation, except for now everything has to be scaled by a polynomial of 1 degree less, and you go through the exact same argument that you went through with Gauss, and you get the fact that it can integrate a polynomial of degree 2n minus 2 or less. So the last thing I want to talk about today, because I'm not going to have any time to do anything else, is the LGL points. Suppose now that tau 1 up to tau n are chosen as tau 1 equals -1, tau n equals +1, and tau 2 up to tau n minus 1 are the roots of p n dot of tau. So now I've got 2 points that are constrained. These points are called the LGL points, or the Legendre-Gauss-Lobato points. Okay? Now, with the LGL points, both endpoints are constrained. And n minus 2 points were chosen as the roots of p dot n minus 1 of tau. So that means that now I've knocked off 2 degrees of freedom from this whole thing, that LGL can integrate a polynomial of degree 2n minus 3 exactly using the n LGL points. So what we've established today is that if you choose these points to be associated with the nth degree Legendre polynomial, or the roots of nth degree Legendre polynomial, or some linear combination or derivatives of the nth degree Legendre polynomial, you can get very high accuracy approximations in the integral for many fewer points. If you compare that now to a typical low order integrator. So take a typical low order integrator, like a rectangular rule integrator. A rectangular rule integrator, if you double the number of mesh intervals, you only increase the accuracy by, so the accuracy of, let's suppose I break an interval. Let's say I've got a bunch of intervals on let's stick with -1 to 1. I take -1 to 1. I break -1 to 1 into a bunch of evenly spaced intervals, each of which has a width h, right? So they all have the same width. If I halve the width, right, the accuracy of that integration scheme is order h, right? If I make h smaller, it's still order h. So even if I double the number of intervals and make the interval width half, I'm still only as good as order h. So by doubling the number of support points in the interval, I've only increased the accuracy from h to 2h, right? So I've just, by increasing the number of mesh intervals or the number of support points by twice, I gained very, very little in the accuracy of the integration scheme, right? Now, I could, instead of using a rectangle, I could use a trapezoid. But a trapezoid is still only slightly better. It's only accurate to order h squared. So if I take a trapezoid rule and I break the number of trapezoids, if I increase the number of trapezoids by a factor of 2, I still only get something that's order h squared accurate. It's just that it goes from h to 2h, or h squared to 2h squared. So I never really gain much in the accuracy by increasing the number of points by a factor of 2 or a factor of 4 or a factor of 8. Even though I did a factor of 8, my factor of 8 only increases my accuracy by a factor of 8. That's all it does, right? Whereas with Gaussian quadrature, if I add one more point to the number of support points, look at what happens in the accuracy. So let's do a little table here so you can see what's going on. All right? So let's suppose that I take, I'm not going to start with one. I'm going to start with 2 because this kind of makes number of LG points, and then accuracy or exactness. Exactness of degree. Okay. So let's suppose I take 2 LG points, right? So this is n, the number of LG points. So what's the exact what degree polynomial can I integrate exactly with 2 LG points? Three, right? 2n minus 1, 3, right? What if I increase to 3 points? Now what do I get? I get 5. What if I increase to 4 points? What if I increase to 5 points? What do I get here? I get 9. What if I increase to 6? You notice something? If I increase to 7, what does this become? 13. Look at what's happening to the gap. The gap keeps getting bigger, right? Every time I add one LG point as a support point, the gap between the degree of the polynomial that can be integrated exactly and the number of points increases every time from the one before it, right? Here the gap is 1, here the gap is 2, here the gap is 3, the gap is 4, the gap is 5. So by the time I get up to a 7th degree, I use 7 points, I can integrate a polynomial of degree 13 exactly. If I was to do the same thing with a rectangular rule, the order of the accuracy would not increase at all. All what increases is the factor in front. The order of accuracy stays exactly the same. But the order of accuracy here grows significantly faster than the number of points grows, right? So by adding a very small number of Gauss points to my quadrature approximation, I get a much higher accuracy approximation in the resulting function. You don't get this if you use trapezoid or if you use a rectangular rule. You get those always stay the same order. The only thing that changes is the factor in front by however many intervals you have, right? So you never increase the order of accuracy. The order of accuracy increases tremendously as you add points here. So the message that I'm trying to deliver here is that when you use low order integrators, you get low order accuracy. When you use Gaussian quadrature, you can get a lot of bang for your buck. Without using a lot of points, you can get a very high accuracy approximation. So you can see that now, let's suppose you want to solve an optimal control problem. In an optimal control problem, we're doing this by discretization, and we've been talking about collocation methods. Now, if you were to use these types of points to do your collocation, clearly, if you did it right, you'll be doing Gaussian quadrature integration, right? Because I've got a differential equation, x dot equals f of x, u, and t, that needs to be integrated. I have a cost function, which has a Mayer cost and a Lagrange cost. The Lagrange cost needs to be integrated, right? So I've got 2 functions in there that need to be integrated. So integration clearly is a big part of solving an optimal control problem, right? So if I need to integrate the differential equations and I need to integrate the cost, I want to use an approximation for the integral that's as accurate as possible. So these Gaussian quadrature rules can be used to do that. There are other things that are going to come out of this when I actually start going through these methods, which is they're actually very easy to implement. So you can actually set them up on a computer quite straightforward, and you can implement them. So if any of you want to use these methods for your project, you'll actually see that when you actually start setting them up, they're not hard to set up at all. That's just a byproduct of the way it's done. It's by accident that they turn out to be very simple to implement. It's a really nice thing that they are simple to implement, because now you can solve pretty complicated problems pretty quickly without having to do a whole lot of work. All right, but But that's the implementation side of things. From a theoretical standpoint, they have very high accuracy, which is why we want to use them. So what I'm going to do on Friday is we're going to start talking about the different pseudospectral methods now that I've laid out this particular framework and given you a rationale as to why Gaussian quadrature is a good thing to do. We'll take the next step and we'll talk about how we actually use these to construct numerical methods for solving optimal